I'm going to present here a brief introduction to multiple chemical reaction. We have more than one reaction taking place at the same time. I've indicated here two reactions in parallel where a reactant may go to a desired product and a secondary product formed same time, or it may go to an undesired product. And so what becomes very important in chemical reactors is what is the selectivity for the reaction, namely what fraction or what percent of the reaction goes by our desired reaction pathway. So we might define selectivity as in this case, this is a molar flow rate of our product D divided by the molar flow rates of D plus U. So this corresponds to the total amount of products formed, what fraction is our desired products, and often we multiply by 100 and use percent to talk about selectivity. This would be for a flow reactor. If we were looking at a batch reactor, we might look at the final number of moles of D in the reactor over the number of moles of D plus U, where this is just total moles. So in general, we might think of selectivity as the rate of formation of our desired product, D, over the rate of formation of all products. We may have 3, 4, 5, and more reactions taking place simultaneously. So selectivity often becomes more important than rate of reaction, having a larger fraction of our reactant go to product that we want rather than something that's not desirable, something that's a pollutant, something that is worth less than our original reactant. And selectivity then is affected by concentration of reactants, affected by temperature, affected by which catalyst is used for the reaction, and catalyst change selectivity significantly. It's affected by the type of reactor, since the type of reactor affects concentrations, or the mode of reaction of the reactor. It's also affected by how much reaction, what is the conversion. If we have 90% total of our reactant used up, we're likely to have a different selectivity than if 10% is used up. So let's look at some of the specifics of how these things affect reactions. Let's look at the effect of some of these variables on selectivity. A higher reactant concentration favors the higher order reaction. What this means, if I have two parallel reactions, I desire to make the product D. Let's say the rate of formation of D is second order in our reactant concentration, but it's first order for the undesired reaction, first order in the concentration of A. Then if I have a higher concentration of A in my reactor, I'm going to favor this reaction. I'm going to have a higher selectivity by picking conditions that favor higher reactant concentration. It can look likewise at temperature, and a higher temperature will favor reaction with the higher activation energy. So what does this mean that we favor the higher activation energy? I'm looking at rate here. Let's make this the log of the rate plotted versus the inverse temperature. High temperature at this end, which means as we increase the temperature for most reactions, rate constants go up exponentially, and so we would have a straight line representing the log of the rate versus temperature. For a different reaction, the line might look like this. This is the one with the higher activation energy, has a steeper absolute value of the slope, and so as I go to higher temperatures, I'm going to favor this reaction over this reaction. So where these lines cross depend on the rate constant, the pre-exponential factor in the rate constant, but we're favoring the reaction with the higher activation energy. Well, the type of chemical reactor that we use certainly affects the selectivity, and so we're just looking at some basic ones here. Batch and a plug flow reactor, these start out at the high concentration of reactant and then it decreases. So if we want to favor reactions with the higher concentrations, we want the selectivity towards the higher order reactions. Batch and plug flow reactors give us that advantage. With the CSTR, we're running at low reactant concentration, and so if we want it to favor reactions that are low order, CSTR has an advantage. CSTR, we immediately decrease the concentration of reactant. If we have a reactant Ca0 coming in, we immediately drop to our final concentration inside the reactor. There is one type of reactor that allows us the potential to control selectivity by how we run it. So if we have, for example, two reactions where A plus B can react to form desired versus undesired products, and let's suppose that the undesired reaction is first order in A and first order in B, whereas the desired reaction is first order in A, but it's second order in B. So this means we're going to favor this reaction, have higher selectivity if we can keep the concentration of B high. And we potentially could do that in a semi-batch reactor by starting out with so many moles of B in the reactor and then flowing in A. So we're keeping the concentration of B as high as possible, and we're going to favor selectivity towards this desired reaction. And certainly one way that we have tremendous potential control over selectivity is with catalysts and picking the appropriate catalyst. So what you can imagine is we can change the relative values of these rate constants by finding a good catalyst, a catalyst that makes this reaction go much faster than it makes this reaction go. And catalysts can have tremendous effects on selectivity. The final example we will look at is a series reaction. The previous ones have been parallel reactions. So in a series reaction where this is our desired product, something like partial oxidation, for example. So the space-time, the reaction time, affects selectivity, and that can be the most important variable, is the space-time. So the other way of looking at this is how much conversion do we have? So just a simple drawing, the idea is if A is reacting, say, by a first order reaction, so its concentration decreases exponentially with time. The concentration of B increases as A reacts, but as the concentration of B gets higher, then the rate to form C increases, and eventually we go through a maximum and we start converting B to C. So the residence time in the reactor, here we have a relatively high selectivity. If we run it to much higher conversions, we have a relatively low selectivity. So we might imagine that we could get higher selectivity in a plug flow reactor than a CSTR, and of course it depends on what the conversion is in that reactor.